So another this is the map now. Active faults in the Philippines. So in trenches in region 1, in CAR or Cordillera Administrative Region, in region 2, in region 3, in region 4A, active faults in region 4B, in region 5, in region 6, in region 7, or may nakadaghan ani nga slide, in region 8, in region 9, si tawi-tawi no, so in region 10, region 11, region 10, Bukidnon, no. So na ay active fault, I don't know if it is active, but na ay fault sa Valencia. Not sure. Try to unsa na siya nga website is GeoHazard sa Philippines, GeoHazard. I'm not sure, nakalimot ko sa kuan, but makita ninyo dito no ang mga faults no. Makuan din niyo ma-zoom out. Sakto ba ko? Yes. Kung asa to dapit ang mga active faults and trenches in region 11, in region 12, and in region 13, and active faults trenches in ARMM, and active faults in NCR. And yes, for the computation of the design base shear, this is the formula, this one. Yeah, for example, we have this building or frame of the building. This C sub T, this is this one is the computation formula for the period. This is H sub N, no, or the height of the building. For example, this one, the C sub T for steel. If this is steel, your C sub T, this is the coefficient of, yes, this is given in the code, no? This is the coefficient 0.0853 for steel, special moment resisting frame, no? Then substitute the H sub N, this is the height of the building from the ground, and the power of 3/4, no? That is 1.093 second. Pasabot aning period, this is the time nga mo drift or musuy ang building 1.093 second, mubalik siya sa ang original nga position if there is an earthquake. And if your building or structure is concrete, now your C sub T coefficient for the T or period is 0.0731. So substitute, this is the value 0.937 second. Notice that mas gamay siya no kaysa sa steel ang imuhang structure, because ang steel is flexible, no, ductile ang steel than the concrete. So tendency is that mas taas ni siya og drift. I mean mas taas maabot ang structure og drift, no, kay mas flexible man siya kaysa concrete, no. So mao na ang gamay ra iyang period, no, pagbalik sa original nga position. And we have this for other systems. The coefficient is 0.0488. So the period is only 0.626 second nga magbalik siya sa original nga position, no. We have this example for a given. We have zone 4. So the your Z is 0.4. The seismic source type is A. And distance to seismic source is 10 kilometers. So seismic source, this is, pasabot ani, this refers to your active faults, no? Or yes, seismic, no? Sa active faults. Soil profile type is S sub C. And the importance factor is R is 1.0, no? Depende na siya sa inyong occupancy. R is 8.5 for the special moment resisting frame for concrete, no? And the total weight of the building is 7,300 kilonewton. So we have to determine the structure period T using method A. For concrete moment existing frames, C sub T is 0.073. Yes, for concrete moment existing frames. So compute. And the height of the building is 25, no, from alright, from footing. So that the period is 0.81 seconds. So find the near source factors n sub A, n sub B from the tables for seismic source type A, and distance to near source is 10 kilometers. So your n sub A, this can be from the table in the previous slides now. N sub B is 1.2 according to this given condition, no, of your building. And determine the seismic coefficient C sub A and C sub B from table for soil type S sub C and zone 4, no? So the computation of C sub A is 0.4 N sub A and 0.56 for CV is 0.56 N sub B. So this is can be found in the table also. If you remember, ganina, no? Taas na siya. So anyway, so, ano siya? Your C sub A is 0.4 and C sub B is 0.62672. So, for the total base shear computation, we have to compute the general formula, no, in CP208-4. The answer is 712 kilonewton, but we have to compare this one for the other formula for the total design base shear. This one should not exceed the following, this formula, no? In substituting those values, the coefficients, you will get this value for this type for this specific formula, 858 kilonewton. But the condition is that need not exceed, no? Should not exceed this one. So this will govern the design, and this will not be less than the following. So kato siya, this one should not be less than this one, no? So if you try to find the base shear for this specific formula, the answer is 321 kilonewton, and which is less than, this one is less than the this one, no? So still this one will govern comparing this answer of this formula. And in seismic zone 4, the total design base shear shall not be less than this formula. Substituting the values, you will get the 330 kilonewton, which is less than in the general, no, formula for the total design base shear. So this this answer will govern you, no, in the design. So the total design base shear V shall be distributed at different floor levels according to the following, no, this formula. So this is the total design base shear minus F sub T. F sub T is 0.7 times the period times total design base shear V, when period is greater than 0.7 seconds. So we computed the period previously as 0.81 seconds, which is greater than 0.7 seconds. So else kung less than siya, your F sub T should be 0, no? Then mass at floor level, and h of x is the height of floor from the ground level. This is the dynamic analysis response spectrum. No, this is the spectral acceleration, and the x-axis is the period. No, so response. This is the behavior of the acceleration. No? When you have to use the dynamic analysis, no, in the response spectrum. period. Anyway, for the load combinations, buildings and towers and other vertical structures and all portions thereof shall be designed to resist the load combination in NICP Section 203. The critical effect can occur when one or more of the contributing loads are not acting. So we have this notation for the load definitions. No, we have D, the dead load; E, the earthquake load; E sub M, this is the estimated maximum earthquake force that can be developed in the structure; F is the load due to fluids with well-defined pressures and maximum heights; H is the load due to lateral pressure of soil and water in soil; and L is live load except roof live load, including any permitted live load reduction; and L sub R is the roof live load, including any permitted live load reduction. L is the live load except a roof live load, including any permitted live load reduction. L sub R is the roof live load, including, I think, yeah. R is the rain load. T is the self-restraining straining force that affects rising contraction, expansion, temperature change. Now, ang T. W is the load due to wind pressure. So we have these load combinations for the reinforced concrete design and the steel design. So you have this 1.4 dead load plus F. So F is the this is the load of the fluids. Pero kasagara, we will neglect the F, no? And the T. So mahimo aning 1.4D, then 1.2D plus 1.6 live load plus 0.5 roof live load, no? Or 1.2 dead load plus 1.6 live load, no? So these are the load combinations. Then the F sub 1 is equal to 1.0 for floors in places of public assembly for live loads in excess of 4.8 kPa or for garage live load, and 0.5 we have to use 0.5, no? There is F1 here for other live loads. Then the load combination for strength design, the application of strength design load combinations that involve the seismic load E for the moment existing frame is, we have this example, we have this Z is equal to 0.4, C sub A is 0.44, importance factor is 1.0, the rho 1.1, and F sub 1 is 0.5. Is this? Alright, I think this is the computation of the factor loads. We'll try to discuss this one, no? Strength design. So we have this example. Then we are required to determine or find the strength design moment at beam A and strength design axial load and moment at column top C. Moment. So combining those moments, we have M sub A. Alright. And yes, no, might discuss one separate discussion of that example. So goodbye, and kindly study for this topic.